Welcome everyone to the first seminar of the semester. Today we are very happy to have Sara Murciano from Caltech, who will be telling us about boundary transitions from a single round of measurements on critical systems. Yeah.
And thanks a lot for the opportunity of being here. It's a pleasure. Yes, so the idea is to tell you what I've been doing basically to Caltech, so roughly 2 years ago. So it's a collection of projects and ongoing projects that I've been doing with Pablo, you and Stephen, who are also at Caltech, Roger and David, who are Roger is in Pittsburgh University, David is in the Weizmann Institute, and Jason, who is my advisor there. So I will start. I will try to motivate a bit why we were interested into this topic, but at any moment, you can interrupt me for questions and anything. Why measurements? And why we were interested in studying measurements on critical systems? And actually, when I moved to Caltech, studying measurements in quantum many-body systems was already quite an active field of research. There are several motivations behind this that I'm going to present. But the main idea is that we are trying to use measurements, or many people before me have tried to use measurements in order to generate interesting phenomena rather than just to probe quantum matter. So it's a bit a change of paradigm in how we see measurements. And
you do measurements to measure phenomena. Here you said something interesting. You do measurements to create phenomena or something?
Exactly, yes.
That's unusual, right? Okay.
It's unusual.
Okay.
And this is why, this is what makes things much more interesting. For instance, we'll see, I will focus on specific transition, like what I call boundary transition. But there are different phenomena that you can generate and that were studied.
Well, why do you call it measuring phenomena rather measurement rather than just experiment? It's like particle physicists call light particles to observe phenomena. You use the terminology measurement to create phenomena. So.
Yes, because they are really like projective measurements. It's the operation that we implement are projective measurements, which is then like when you measure the charge, it's a measurement. And the example of this novel quantum phenomenon indeed arises in a dynamical set. Like, for instance, take a system, initialize it in the wave function that you prefer, and then you let it evolve with a given Hamiltonian. Now, this evolution, this dynamics, what creates is, what does it's creating entanglement. It creates entanglement. And you need, for instance, to start from a state which has not so much entanglement, and then you let it evolve. The evolution will create some entanglement. We have some, we have these. We would have naturally entanglement growth. But if during this dynamics we also perform some measurements, then I think on applying a projector on a wave function, the effect of this projector is to kill somehow the entanglement of the wave function itself. Eventually, you can think that if I apply a complete projector on a many-body wave function, it will turn it into a product state, depending on the measurement outcome. So you see that these two phenomena, like unitary dynamics on one side and projective measurements on the other, can compete, and due to this competition, interesting phenomena in the entanglement behavior can occur. For instance, in this specific setting, between entanglement between unitary evolution and projective measurements, the entanglement can go from an entanglement growth to an entanglement saturation, passing through a logarithmic growth. So this is a kind of funny phenomenon that arises in this kind of context, which has been also observed. Like using quantum simulators, it was possible to probe this competition between dynamics on one side and projective measurements on the other. a picture taken from this work done in the group of Munich, where basically by studying the variance on the entanglement, they were able to observe this entanglement transition. And so I've given an example of a novel quantum phenomena that occurs in out of equilibrium settings. But interesting phenomena can also appear in static setups. For instance, suppose that I have a state which is called character state, characterized by a flipping interaction where we have z at z equal to 1. Now, if I perform measurement on these red sides, I perform measurement on in the x basis, and for instance, I read plus, minus, minus, plus, minus, and then I flip the measurement, I flip the spins on the other sides, depending on the measurement outcome that I read on the neighbor side. Then what I can get is a state, where I have all up plus all down, which is an example of long-range correlated state. So this is a very example in which measurement one can create long-range entangled states, but there are many other examples concerning more complicated wave function where this can happen.
For the measurement-induced stuff, what does it mean by transition? Like, does it have like critical exponents and like discontinuity?
So the main feature that happens in this transition is that the entanglement grows from an area low, volume low, meaning it's linear in the subsystem sides, to an area low, meaning that it's constant in the subsystem sides.
So is there some derivative of it that has some discontinuity?
At the transition point, the entanglement grows logarithmically.
Okay.
Function of the subsystem. So this is that continuity that you can see in there. But indeed, it's not clear whether this can be described by some like new universality class or not. And indeed, this is what people are looking for, like use phenomena to, for instance, generate new set of states, states with different like critical exponent. Yeah.
Thanks.
Can you explain a bit what the color coding is? So am I to understand that each point is like a spin, can go up or down?
Yes.
The blue is plus, is it?
No, here it's just some, it's just a wave function that has to satisfy this constraint that it is described by an Hamiltonian three-spin interaction. And then you do measurements on the red sides in the x basis.
Okay.
And then based on the measurement based on the measurement outcome that you have, you flip the spins.
On the blue ones, okay.
So these are, and there is almost forgot. I forgot also another very well-known problem in which measurements play a crucial role, which is a quantum teleportation. No, like we have Alice and Bob, and Alice decides the function to Bob without telling to Bob explicitly, this is my function. And the way in which this can happen is by creating an entanglement between Alice and Bob. Then Alice performs a measurement on her qubit, and in this way she can communicate, she can send the wave function to Bob. So by using entanglement, measurements, and classical communication. So measurements play a crucial role in all of these phenomena. So this is a bit a slide in which I want to motivate why should I care about doing measurements on many-body systems. And specifically what I'm going to describe today is what we call measurement alter criticality. And the first pioneering work about this topic actually has been done in Berkeley in the group by Ehud Altman, where they studied the impact of measurements on a Latinger liquid or a compact boson. And the idea is to understand how the rigid properties of critical systems are modified once we perform measurements. Because we know that the critical system, one-dimensional critical systems, are characterized by a logarithmic growth of the entanglement with a specific prefactor of the logarithmic term. They're characterized by a specific power law correlation function with the fixed, rigid power law exponent. And when I say fixed, I mean that these numbers are fixed by the specific universality class that we are considering. And so now the question that I want to ask is how these numbers, how the entanglement growth is affected once I perform measurements. Okay, so the plan of the following parts of the talk will be to first introduce the protocol of measurement alter criticality, how we think that this can be realized. And I will start by a very simple model, the ground state of the Ising spin chain to its critical point, in order to understand a bit what is the impact of measurements in this case. And then I will show how the results and the techniques that we use for Ising actually can be used for different kind of critical systems. In particular, I will show the results for the critical Ising model and the three-state POTS model. And finally, I will draw some conclusions.
Roughly, what does weak measurement mean, roughly?
So it's a softened version of a projector. Like rather than having a projector like bracket, I write it as an exponential of some operator that in the limit of strong coupling gives me a projector. Mm-hmm. But I will
explain. Okay.
I will explain it, yes. Yeah, but you can think of it as like not a full projector, but something a bit softer than a project.
If you didn't tell us this, naively we would think, oh, it's a low energy being imparted on the system compared to its typical energy levels, but there's nothing to do with that apparently, right?
No.
Okay.
And I will also try to explain why you need to do with measurements. Okay, so first of all, the model, just to be all on the same page. I have in mind this Hamiltonian, which is the Hamiltonian of the Ising spin chain. So here Z and X are the Pauli spin operator. And what is the phase diagram of this Hamiltonian? So if I don't have a transverse field, so if H is equal to 0, then I have two degenerate ground state, all up plus all down. And the system is in the ferromagnetic regime. Then I can turn on my transverse field. And so it means that this will induce some superposition of configurations with the flipped spins. And when H is equal to J, where J is just an energy scale, the special relation of this model becomes, the energy becomes, the spectrum becomes gapless, and it will be described by a conformal field theory. And then in the regime in which H goes to infinity, basically, if I neglect this term, the ground state of this Hamiltonian will be given by all the spins pointing in the x direction. So this is the phase diagram. So we go from the ferromagnetic to the paramagnetic regime. And both at the critical point and in the paramagnetic regime, the system is Z2 invariant, meaning that if I flip the spin, the Hamiltonian flips. Now, in principle, I may apply a projector here, and this would be a measurement. But if I do this, a projective measurement will turn this state into a product state. And the product state has zero entanglement. It's not interesting, right?
Is this the definition of projective measurement?
Yes. You just apply a projector, and so you get a bunch of like spin up, down, according to the measurement outcome.
From a single state, you get multi-states, you say? Or?
No, it's one state.
Yes.
But for instance, I can project into the wave function with all the spin up. No? So I have a wave function where all the spins are up, and this is just a product state.
It's a pure product as opposed to products plus products plus products, right?
Yeah, exactly, yes.
Uh-huh.
Because you don't have a superposition of states. Uh-huh. It's like if now your critical wave function, you can expand into a basis, no? And each element of the basis is a given configuration. Okay. It's like if you pick up one of these.
So that's why it's called projective. You get one. Okay.
But this is not interesting, so we have to do something else. And how can we do something else? It is the following. I will consider some additional degrees of freedom. In our specific setup, we consider also the ground state of the Ising speed chain, but now tuning its paramagnetic phase. So we don't have a critical system here. And then, so this is the first step of our protocol. And then at this point, we entangle the ancillary degrees of freedom with the system. And the way in which we entangle them is by applying some on-site unitaries. So in particular, the form of the unitaries that I will consider can involve X on the system and Z on the ancillary, and Z on the system and Z on the ancillary. So you see that these two different operators, X and Z minus 1, that I'm applying on the system, will have a different impact at the level of the Z2 symmetry of the system, no? Because X respects the Z2 symmetry of the Ising model, while Z minus 1 doesn't.
Is this an actual experiment people do?
It's a protocol, and we are working on the experimental implementation.
And in achieving this, you use, I suppose, fields, electromagnetic fields, or what do you do to achieve this kind of perturbation?
So, okay, in order to get exactly this result, the most experimental friendly way that we found is to prepare a system, which is a Rydberg, it's called, they are called Rydberg arrays. So it's a model where you can tune the parameter such that you realize the Ising universality class. Like we don't, the microscopic realization is not in terms of this Hamiltonian, is in terms of a different model, which has the same low energy description as the critical Ising.
Rather than the theory side, I was asking the experimental side. I mean, what in reality, what kind of physical system in the lab you have? Is it a metal? Is it a...
These are Rydberg atoms. They are
like an array of atoms, right?
It's an array of atoms.
Array of atoms, and then you
tune by using some lasers, you tune you tune it exactly to the Ising.
So lasers is the key tool here then.
Yes.
Okay, thank you.
And then you have to do measurements.
Oops. Thank you.
Yeah, indeed, we are currently working on it because I will tell you several problems that can appear if you think.
Surely you don't do the experiments, do you, yourself?
Not even the numerical simulation, as to say. Okay, so we have a system, we have an ancillae, we entangle the system and the ancillae through some unitary operators. And then we perform a measurement on the ancillary degrees of freedom. We measure in the X basis. Now, the reason for which I choose to measure in the X basis is because here this unitary has a ancilla, so I want operations that don't commute among each other. But in principle, you can change, you can choose the unitary you want and pick up the measurement basis you want. This is just to fix the ideas and to focus on a specific project.
Slip between these two different use in the product you can. Is it like a, should I of this as being some kind of an evolution that's happening for the entire system?
You can think of a unitary evolution at this level before any measurement.
Yes.
After you apply the measurement, this is non-unitary, so you can think as any evolution.
Of course, but in the product, so when you are
you can think of U as a time, let's say.
I see.
And actually, U is the parameter that controls how weak your measurement is, because the more the two chains are entangled, the more your system will feel the impact of measurements on the ancillary degrees of freedom. So small u means that you have weak entanglement between these two chains, because the impact of the measurements is
right. Actually, I'm a bit still confused about this step 2. So how is this actually happening? If you, even theoretically, if there is somebody from the outside is tuning these U's.
There is somebody from the outside. Yes.
Right, and you are not interested in how that effect can.
Yes, we are indeed. Okay, let me do a
Yeah,
step
sure,
more, and
sure.
I will tell you how the U enters.
Or maybe the question is this a random variable that you said we are doing 1 or 2 because you have 2 different evolution here?
You mean I can choose between this one and this one? Yeah, I can choose between these, and I can choose among any unitary operator that I want. But I think he's asking about these parameter use.
Yes, but okay. Go ahead.
Yeah, I will show the slide. The main reason for which I've chosen these two is because here I present the symmetry of the system because there is X. And here I break the Z2 symmetry of the system.
Mhm.
And we will see how these two different choices will have a very different result.
And what is the strength of the entanglement in this formula? Is it U?
U.
Okay.
Yes. So basically, U equals 0 means that you don't have any entanglement, so you don't expect any impact from the measurements. And U equal to power 4 is when they are maximally entangled.
Is there a range for U I should think of?
We will focus in the regime of small u, which is what
Small
we
u, okay.
weak
Order 1 U would be strong entanglement, I suppose. Order 1.
Yes.
Okay.
Okay, so far we have 3 steps. Initialize system plus ancillary degrees of freedom. Entanglement between the system and the ancillary degrees of freedom. Projective measurement of the ancillary degrees of freedom. This is the projector, and this A tilde denotes the configuration, the measurement outcome that I'm reading. And okay, this is just some normalization factor. So now what is the next step? The next step is trying to understand this post-measurement wave function. And we can do a polar decomposition of the non-unitary operator that we get, such that we write it as a unitary times a non-unitary operator, which is what we are interested in. And this non-unitary operator is what imposes my weak measurement, because I'm interested in the regime of small u. And this is the post-measurement wave function. So let me stress, coming back to your experimental question, here I'm post-selecting a specific measurement outcome, meaning that among all the possible 2 to the L, where L is the system size configuration, I'm choosing the most likely one. Even though it's the most likely one, you can imagine that since there are exponentially many of them, the probability of picking up exactly this most likely measurement outcome is very low. So this was one of the main challenges that we had to address in order to think of an experimental proposal, an experimentalization of this problem. Theoretically, I can say that I both select the most likely measurement outcome, but to an experimentalist, I cannot tell him that he has to pick up exactly that one. So we have to find a way in order to maximize a lot the post-selection probability. But still, I think it's a very nice exercise to do because it's how we understand really what's going on after these wave measurements. Okay, so this is our post-measurement wave function. We have this unitary operator acting on the original system, and I want to study the properties of this post-measurement wave function in terms of entanglement or correlation function. How can we do it? I will use I'm interested in the continuum formulation of the problem. And what does it mean? So
Excuse me, post-measurement state you are talking about, post-measurement state. But that itself requires a measurement, doesn't it? So
yes, indeed, M, the non-unitary operator, somehow combines the unitary plus the projective measurement that I was doing.
but whatever you get, you're going to apply another M because you're going to measure the post-measurement state. So what's the difference between that measurement and the original measurement? I'm confused.
Well, at this level, I have a post-measurement wave function, and then I want to compute, for instance, the entanglement of this post-measurement state, or I want to compute a correlation function on this post-measurement state.
So it's a new kind of measurement.
Yeah, it's a new kind of measurement.
Okay.
Yeah. Like also in the experiment, what you do, you first have to construct this one, and then you have to measure the correlation function. That will be a further step.
It's like kicking a ball in the air and then study its velocity, something like
But
that.
it's also what you have to do.
Okay.
You have just a wave function. In the end, you only have to start using an interoperator. So how can we compute the properties of this post-measurement state? Now the approach that I'm going to use is very simple. Suppose that I have an observable A, and I want to compute the correlation function of this observable on a critical state, side C. Now I can think in terms of the path integral formulation of the problem, no? Where I have an imaginary time evolution from -infinity to 0, which corresponds to the preparation of the HET. Then I will insert my observable A, and then I have an imaginary time evolution from 0 to +infinity, which corresponds to the preparation of the Brown. This is the path integral formulation for this correlation function. Now, the only difference, if I insert this measurement operator here, is that once I hit the line at tau equals 0, I also have to insert this M here, which basically will act at all special points, but only at tau equals 0. So at the end of the day, performing a weak measurement corresponds to introduce a defect line on your x tau space-time. In particular, if this defect line doesn't break Lorentz invariance, I can also, let's say, rotate it along x equals 0, and then I can think of my weak measurement as an imaginary time quantum impurity.
So if you didn't have a small u, would the thickness of the defect sort of grow?
No, what is the problem? That I want that my field theory description of the problem is under control.
See.
So if this function f of u is not small, basically I cannot go to the continuum limit. At the end of the day, numerically, for instance, we can check for any value of u how our prediction change, and we have seen that they don't change. But strictly speaking, if I just want to rely on a field theory setting where all my continuum formulation works, I cannot take u to be too large.
So high energy theory is always interested in imaginary time and rotation, but quantum information, I mean, you need unitarity. So how come that because you're losing unitarity if you just...
We are losing unitarity, yes. And indeed, to solve this problem, we are using say some known results that people have found in other contexts, like just decline defects problems to evaluate entanglement correlation function. Yeah, but recently the idea of using measurements to prepare new states, new kind of states, or finding novel phenomena, it's quite common in quantum information. We like doing measurements because it seems quite an effective. I mean, anyway, we have to do measurements always, so just let's use them for useful.
So the word non-unitary should not scare us then.
No,
It doesn't mean the holy principle is violated.
I think also like there are lots of studies on open quantum systems, where you have dissipation, decoherence, because we want to start to understand how really things go in the lab. So we cannot think about an ideal preparation of a quantum state because there will be always dissipation, decoherence, and what they do,
So if you take everything into account, unitarity is never violated. But if you consider an open system, then it's okay.
Yes, yes. It's much closer to a real...
Are you happy now with this? Okay. He's happy.
Still measurements. Even if you take everything into account, you measure something and then it's non-unitary. The measurement process itself is non-unitary.
But shouldn't measurements be consistent with unitarity?
No,
They are not.
that's
That's the
the main
measurement problem.
challenge of
Yeah.
quantum mechanics, Sergey. So measurement is not non-unitary.
Exactly. Maybe again, like similar formulation of the insertion of this defect line can be found if you apply some, they're called like non-unitary channels to your system, and the impact of this. At the end of the day, always think in terms of defect line. Okay, so now I will I want to show what is the impact of this defect line on this measurement protocol that focuses on the Ising model. And maybe you would recognize some old results that you found like back in the days about defect line problems just applied to different setup. Okay, let's start. And let me start from the entangling unitaries. That's, as I said, preserves the symmetry of the system, and the corresponding post-measurement takes this form. So it's a function of u, sum over j, xj. So this operator preserves the Z2 symmetry of the system. And as I said, I'm interested in the continuum limit of this operator. So the continuum limit corresponds to a defect line that involves an epsilon field. So just a brief recap about Ising CFT. Ising CFT contains three primary fields, the identity sigma and epsilon. And we know a dictionary between the lattice operator on one side and the fields on the other. So for instance, the Pauli operator Z corresponds to the sigma field. The Pauli operator X corresponds up to the expectation value to the epsilon field. Now sigma is scale in dimension 1 over A. Epsilon is scale in dimension 1. So if I do a simple dimensional analysis of this term, since this is a defect line, so it lives along one dimension, this perturbation is marginal. And so I can ask, what is the impact of this marginal perturbation, so of the measurement, on the original system? How are critical properties modified? And in order to understand how they are modified, I will look at entanglement and correlation function. So for instance, let's start from the entanglement. In the Ising model, a critical one-dimensional critical system, in my case, I'm focusing on one-dimensional systems, the entanglement of a critical system grows logarithmically as a function of the subsystem size. So for instance, I have an infinite system. I take an interval of length L, I compute the entanglement between the interval and the rest of the system, it will increase logarithmically. And the factor of this logarithmic term is the central charge, which is another crucial element of a conformal field theory, that for Ising is equal to 1 alpha. And I can ask how this central charge, or better, how does the factor of the logarithmic growth of the entanglement changes after measurement? Since the impurity action is marginal, one can find, and actually in this case, the computation can be done exactly also on the lattice level, that this prefactor of the entanglement entropy monotonically decreases as a function of the measurement strength. So basically, if this is f of u that I'm plotting here, as this f of u increases, so the measurement strength increases, this effective central charge goes to 0. Effective central charge is just the name for the prefactor of this log L term. I call it effective because it's not anymore the original central charge.
Can you remind me quickly what the function f is?
I haven't written it. It's some arcotangent.
It's monotonic with respect to u?
Yes.
Okay.
Yeah, I haven't reported it.
So I shouldn't think this as flowing away from Ising point, right?
Well, it's a marginal perturbation. So being a marginal perturbation, it's like if at any for any u, I have a different fixed point. So I'm still flowing away from the Ising.
Oh, sorry, okay. I thought C equal to half is almost like the lowest central charge, but
Equal 1/2 is
I mean, I sorry, I thought this is like the minimum central charge for the RCFT half.
1/2. No, but indeed you don't have to think of it as a real central charge, like as something that you can find from the stress energy correlation function. It's an effective central charge because it's just the prefactor of the logarithmic term of the entanglement that usually is the real central charge. In this case, it's just called effective central charge. It's not something that you can derive like the answer of these things. But indeed, this is a good point. Like, where does this marginal perturbation brings me? And actually, for marginal perturbation, it's more tricky because any point along this line is a fixed point itself. But we'll come back to for the relevant perturbation, and there the answer is much more clear. Similar result can be found also for the two-point correlation function of the Pauli spin operator. As I said at the beginning, these power law correlation functions are rigid because they are fixed by the universality class of the model that I'm considering. Now, if I apply this measurement and I introduce this defect line, then what we find is that the power law exponent continuously changes as a function of the measurement strength. So the order of parameter z, we go from 1/4 up to -4. -1. So this changes monotonically in the function of u. Only for xx, we haven't changed the power law exponent, but the overall prefactor changes. Indeed, if we scale all of them according to the prefactor, we see that all the lines collapse. So here we have some analytical prediction and we have cross-check with the numerics. An analytical prediction can be run because this operator the Gaussianity of the state, so on the lattice level, it's very easy to pick the properties of the post-measurement tool. Okay, so we have seen that the effect of a marginal perturbation is to slightly measurement alter the power law exponent of the correlation function and the prefactor of the entanglement entropy, this effective central charge. But now we can ask what happens in the other protocol where I have this unitary operator that breaks the Z2 symmetry of the system. Now, the form of the non-unitary operator that we have in this case contains a Z that breaks the Z2 invariant explicitly, because now it's not invariant by sending Z into -Z. And if I write the corresponding defect line in this case, now it will involve a sigma operator. Now the sigma operator has a scaling dimension of 1/8, and so the perturbation is relevant. And so in this case, it's much more clear that I start from a fixed point, which is Ising, and I flow away somewhere else. And now we'll see what is this somewhere else. First of all, if I compute the entanglement entropy in this case, what we find is that the entanglement entropy saturates to an area law behavior, meaning that there is not anymore this logarithmic growth. The effective central charge goes to 0. And why this? Because the presence of this relevant perturbation, it's like if it's introducing a boundary, a cut between the upper and the lower. So the entanglement properties are affected a lot. And if I compute the two-point correlation function of the Pauli spin operator, we find that the power law behavior of this two-point correlation function now doesn't depend on u, doesn't depend on the measurement strength. It's fixed, and it's equal to -4. It's equal to -4. Okay, So we have a state, a post-measurement state with area law entanglement and correlation function of the Pauli spin operator equal to -4. I will say in a moment what is the corresponding fixed point, but maybe if you are familiar with the boundary conformal field theory, you can recognize that this -4 comes exactly from there, from the fact that your relevant perturbation is introducing basically a boundary because it's a relevant perturbation and it's introducing a boundary between the upper and the lower half plane.
So, I mean, is this a specific convention that we have -4 over there and -quarter over there, 1/4?
Yeah, it's just an accident that in this case there is like, for instance, if you look at YY, it was -9/4 and this is also -4. So it's, yeah.
Ah, okay.
Yeah, there is no correlation. Okay, so let me do a brief reminder about BCFT. In general, if I have a point-to-point correlation function, for instance, of the order parameter in a CFT, we have already seen that the power law exponent is fixed by the scaling dimension of the sigma operator, which is 1/8. So in this case, it's x to the power of -1/4. Now, making a measurement, what does is to actually decouple the upper and the lower half plane due to the fact that we have introduced a relevant perturbation. So it's like if I have an upper half plane with some boundary condition. And in general, I can have two kinds of boundary conditions for Ising. I can have some fixed boundary conditions that at the lattice level you can think of as fixing not the configuration of the spin, like up. And if I compute the two-point correlation function, if I'm deep in the bulk, then I don't feel the presence of the boundary, and I feel the power law exponent -1/4. But as I get closer and closer to the boundary, of course, I feel the presence of the boundary, and in particular, if I'm very close to the boundary, the power law exponent becomes -4. Now, the other possible boundary condition that we can have for Ising is the free boundary condition, where I don't impose basically if they are up or down, they can take whatever value we want. And in this case, the power law exponent close to the boundary will be equal to -1. These are just some standard BCFT results for the Ising model. So now, if we compare with the results that we found when we break or when we don't break the Z2 symmetry, in one case we find the power law exponent equal to -4, which is compatible with the fact that now this relevant perturbation basically brings me to the BCFT of the Ising model. So this is where I'm flowing once I apply this perturbation. Now, for the marginal perturbation, the things are more tricky because, as I said, I should just focus on a weak measurement regime. But we have observed that if I focus on the regime of large measurement strength, the power law exponent saturates to -1, which is compatible with the flow to a free boundary condition. But it's not rigorous at all because, in principle, I shouldn't rely on the field theory prediction at that level, but it seems that they match. Basically, BCFT is, if you want, a way in order to understand what is the impact of this of my measurement operation. And how much time do we have?
15 more minutes.
Okay, so I can running out. Okay, so this is what happens for Ising. We have seen how different Z2 breaking and Z2 preserving measurement can have different impact at the level of entanglement growth and behavior of the two-point correlation function. We have been able to, let's say, understand this post-measurement behavior in terms of the corresponding BCFT that this measurement will induce. Okay. Now let's make things a bit more complicated, and let's focus on a different minimal model, which is the tricritical Ising model. Let me start again by the microscopic Hamiltonian describing the system. It was actually a model on the lattice introduced a few years ago by Fendley. You can recognize, so the first term is actually the Ising Hamiltonian tuned at its critical point. And then we are adding a perturbation involving a three-spin interaction. And by properly tuning this coupling here, the system can describe the universality class, can fall into the universality class of the tricritical model. Now, in this case, the central charge is equal to 7/10, while before for Ising it was equal to 1/2. Again, we can write a dictionary between operators on the lattice and the corresponding counterpart. For instance, now it maps again to the sigma field, which has scaling dimension of 3/40, while X maps to the epsilon field that now has scaling dimension 1/5. Let me observe here that before the scaling dimension of epsilon was 1. Now it's 1/5. And so this will make a crucial difference because that one was responsible for a marginal perturbation. I can already predict that the perturbation won't be marginal in this case.
What happened to your H and delta or J, whatever, for?
Oh, I said them equal to 1.
Critical.
Yeah.
Just consider.
Yeah. So this is Ising model. And when lambda is, let's say, not tuned at its critical point, it will, this Hamiltonian falls into the universality class of Ising. If you tune lambda exactly at the critical point, then you realize the different.
Did somebody study if we keep H and J?
I'm not aware of it. I think that you will go away from criticality. Think because this spin interaction, I don't think that can this part, it means that this part won't be critical and all the criticality should come from here. I don't know. I think that you would introduce the gap anyway, because like turning on energy field is like introducing a mass term. Okay, so now we can repeat what we've done before, and I will try to highlight what happening. Suppose that I perform a measurement that again preserves, I think involves X here. The corresponding Fisher operator will be an epsilon. Now, even though it's a symmetry preserving perturbation, this defect line is relevant because epsilon scaling dimension 1/5. And according to the discussion before, we would expect that this relevant perturbation, since it preserves the Z2 symmetry of the system, will bring you to the free boundary CFT of the tricritical Ising model. And indeed, at least at the level of the behavior of the two-point correlation function of the order parameter, we find the power law -3, which is compatible with the TCI BCFT. So this is one case. Now the other case is the Z2 breaking setup. Once again, we have a relevant perturbation of scaling dimension 3/40. And now this relevant perturbation brings me to a different fixed point, which is the fixed boundary CFT. And indeed, the behavior of the two-point correlation function is equal to -4, as we would expect. But now what is the difference? Not that before we had epsilon, which was a marginal perturbation, and sigma, which was relevant. So even though I tried to combine epsilon and sigma, anyway, sigma will always win over epsilon. Now I have that both sigma and epsilon are relevant perturbation. So I can ask, is there a way in which they can compete one with each other in order to create some transition between these fixed and the free boundary condition? So how can I do this? I said I measure Z, so I have a sigma, and I go to the fixed boundary condition, which is a stable fixed point. I have a symmetry preserving measurement, and I flow to the free boundary condition, which is also another stable fixed point. So it seems natural that one can have some intermediate unstable fixed point between these two. And the idea is to realize this intermediate fixed point by measuring in the XZ plane. So I consider the following measurement operator, where basically I am in the XZ plane and I rotate by a given angle omega. What is the impact of this measurement now? So this is my omega, let's say, plane. Again, omega equals 0 corresponds to having just x, so I flow to the free boundary condition. Omega equals 2 pi over 2 means having just z, so I flow to the free boundary condition. Then I can increase omega and or decrease from pi over 2. And what we find is that there is a critical value of omega where my measurement operator, so this one, can flow to the intermediate, to this intermediate fixed point, which is called partially polarized boundary condition. Actually, this partially polarized boundary condition was studied by Affleck 25 years ago. So it's a very old paper. And indeed, he already showed that this partially polarized boundary condition lies between an intermediate unstable fixed point between the free and the fixed boundary condition.
Oh, can you classify all the boundary conditions by using measurements?
Exactly, this is a very good question. The minimal models that we have studied so far, we have been able to classify the most standard ones. Like also for POTS, for instance, I will show it. Also for the Latinger liquid, which is even more tricky, because there you also have the dependence on the Latinger parameter or compactification radius, and also there you can explain through boundary condition, through BCFT. There are some specific boundary conditions, like for both Ising and POTS, there are some new boundary condition. I mean, Affleck and Sara have found so many boundary conditions that one can have, and we were not able to find the corresponding measurement operator. But I think that if you try hard enough, you should find it. Yeah. And as a cross check of these, we always compute the correlation function, and we see that the scaling dimension matches with what you would expect from the BCFT. From the spectrum of okay, let me briefly mention what happens for a POTS model, and then I will draw the conclusions. Now, POTS is a slightly more complicated model because on the lattice we don't have any more spin 1/2 operators. We have spin 1 operators. There we have with U and B. You can see that Q here has 3 eigenvalues, which corresponds to the 3 labeled as A, B, and C. While this operator B basically is responsible cyclically permutes these ABC conditions. Again, we can write down a dictionary between operators and fields. So we have that U corresponds to sigma, which has scaling dimension 2/15, and it's not emission. So usually we, in order to have some emission operator, we have to conceive U plus U dagger, sigma plus U dagger. And B plus V dagger is corresponds to an epsilon, which has scaling dimension 4/5. And yeah, the central charge is also equal to 4/5. So what happens in this case? Well, one case is very simple, like if we apply V plus V dagger, this corresponds to epsilon, relevant perturbation that preserves the Z3 symmetry, because now it's invariant under Z3, not Z2. And this will induce a flow towards free boundary condition, as we have seen for tricritical Ising and Ising. Now, something more funny happens for the Z3 symmetry breaking case, because of course, as you increase the number of possible boundary conditions that you can have, the phenomenology that you can create by measurement is larger. So we have chosen this post-measurement operator, which can be, and it's very long, but in the end, this is the operator that breaks the Z3 symmetry. And these V plus V dagger and V plus V dagger don't change the symmetry of the system, but they are there because we realized that on the numerics, what gives us the boundary condition that we expect. At the theory level, the corresponding action contains this defect line. And for instance, when omega is equal to 0, this defect line will favor the A states. So we will flow to the fixed boundary condition of the Potts model, which is labeled by A, not that I represent here. While when omega is equal to pi, this post-measurement wave function will equally favor the B and C boundary condition. And so we will find the flow towards the mixed boundary condition of the three-state Potts model, which is called BC. The number of boundary condition in this case.
Pi or pi/2?
Pi.
Pi.
Yeah, so there is a minus sign of difference here. So basically the idea is that when omega belongs to these intervals, it will flow to A, B, or C boundary condition. And when omega is equal to the specific values, pi/3, pi, and phi/3 pi, will flow to the mixed boundary condition, which can be C and AB. So you can think of this as a boundary transition between these two fixed points. Yeah, indeed. Before for I don't know, for tricritical Ising, I stressed it enough, but all these intermediate fixed point, it's what I call boundary transition. It's boundary transition in the sense that we have a transition between two different boundary conditions. And so let me back up. So we have seen in detail what is the protocol that allows us to perform weak measurement of Ising criticality, and in particular how different weak measurement of epsilon or sigma can give rise to a very different phenomenology. In one case where we have a continuously varying exponent of two-point correlation function and continuously varying effect in central charge. In the other case, we have a very fixed change of power law exponent and an error law behavior, which can be described in terms of the underlying BCFT of Ising. And we have applied the same technique also to study the measurement criticality of different minimal models, in particular, tricritical Ising model and Potts model. And there, due to the fact that the number of primary fields is much larger and the number of boundary conditions that we have is also larger, using measurement, we can tune between the different possible boundary conditions. So we can find some boundary transition in this sense. And now possible things that we are currently working on, as I mentioned before, we are thinking on how to experimentally realize this measurement after criticality in Rydberg array systems, which are a different macroscopic realization of the Ising and tricritical Ising criticality also. So in principle, both the predictions that I've shown today should be visible, and we have, let's say, a very nice protocol that should do it. Then the question that you have already anticipated, like if it's possible to realize other boundary conditions through measurements, it would be nice to have a much more say broader spectrum, especially about these unusual, unconventional boundary conditions that were discovered more than 20 years ago by Affleck. Finally, some more quantum info application of all these is whether these measurement-altered criticality might have some applications for quantum sensing and quantum metrology. I mean, in this field, the critical systems are already a promising candidate because of their long-range correlation properties. And so one can ask if these measurement-altered systems, which are closer, let's say, to a system which has felt the impact of some non-unitary process that can also be, doesn't have to be necessarily a weak measurement, also the coherence or dissipation, are these wave functions helpful for quantum metrology or not? And yeah, it is so from my side. Thank you.
So is there any connection between all of these investigation with ADS-CFT? Because you mentioned boundary bulk, different regime, and you have different behavior in different regimes. And I know, I mean, you just study CFT, and one can ask, is there a gravity realization of that CFT, or is it possible?
If I'm not wrong, there was a paper about it, but Ising I can look for the reference and send it to you, but yeah, I'm only aware of the CFT story, part of the story. I'm not familiar on the gravity side, but in principle you can ask also. I mean, I don't know enough, so for instance, here, and I can understand if I say I measure, I don't know, the magnetization, so one should understand in the gravity whether it corresponds to. But yes, let's say so far there is a translation from the lattice to the CFT level, and then one should do a translation from the CFT level to the gravity side.
Because when you have this aerial law, you know, one would be tempted to think about gravity all the time.
Only when you have aerial or
I mean, you know, aerial law.
yeah.
Murciano and Stefano Antonini and their friends have a paper about that. They have certain measurements in the boundary and they study how it changes the pieces in the bulk.
Who is where?
Brian Swingle, I think.
Swingle, okay.
And then Stefano Antonini. I think he's
Yeah, Antonini, yes.
and I think a few other people too.
Okay.
Yeah, I remember Zwingle had this kind of one about the teleportation, one about measurement. Yes, interested in this kind of quantum info or gravity type quantum.
More questions? Not, let's thank our speaker again.